Hello all, welcome to a new blog. Uh, in my last blog, I had discussed about the physical planning, the SQL query plan, how a SQL string is actually goes through a certain stages, and then from that it provides it outputs a code which is used to run the program. In this new blog, we will deep dive into how Spark Catalyst Optimizer comes into play and what it does and why it is needed in the place. So at the very big outset, Catalyst Optimizer is a powerful query optimization framework. So this is being used by Spark. What it does is all the things that we had discussed in the last blog, like for logical planning, resolved, unresolved planning, and then so all those things are actually uh, in this blog we will see how those things translate into actual real code. Take an example. Basic thing is each Spark has two APIs. One is the data frame API, the other one is the RDD API. Data frame API is for us to use. This is where all the optimization kicks in, and then it gets translated to execution for RDD. And that's where things happen. So here, if you see, the Spark core is an RDD. On top of this is the Catalyst optimizer. So whenever we write we write any data frame or SQL, after being passed, it goes through the Catalyst optimizer, and that outputs an operation, RDD operations, which if we would have directly written ourselves might not be that performant. So this is where the SQL, this is where the Catalyst optimizer plays a critical role. As we had discussed in the last call, last video as well, that rule-based optimization, cost-based optimization is what the query optimizer does. It also has some tree transformation, which is something that is a representation of how the plants will look like. So this is uh, this is the optimizer also works with the Tungsten execution engine, which is nothing but the whole stage code gen part that we were talking is part of that. And then it's code generation is handled by there. So we will see how the code also looks like with an example, not this one. Uh, this example that we have is basically it is what is happening is we have a join. Basically we have two data frames, and based on certain things we are doing a join, doing a filter, then adding a column, selecting that particular column, and then doing an aggregation on top of it. So this is pretty simple Spark code uh, that we are trying to see how it will go through that Catalyst optimizer and how the plans will look like. So in case here, a summary is that we are joining on ID1 and ID2 columns, and we are doing a filter, we are doing a projection of a column V, and then we are returning back the results, the summation of the V. This is what we are doing. So basically, there are a few things that we have to do. So for example, this what we say is lit1 plus lit2. This is nothing but an expression in Spark. So this is what is saying that this 1 plus 2 plus t1 value is nothing but an expression. Attribute is like the t1.id or column generated is an attribute. Query plan that we will see what plan is used for what kind of operation. Entry is nothing but list of nodes, objects which have children's, and the transformations are executed on those, and then we create a single, we get a rules that gets applied to the tree so that we get an output. So this data frame API call can be translated to a SQL expression. That is nothing but, for example, what we are doing is select some V from select T1.id. This we are doing with column, and then we set a join from T1 T2 where T1.id and T2.id are same, and that's this filter. Okay, this is basic SQL statement that we are trying to see how it will go through different uh, plan generation and optimization processes. So when we say select SMB, this as I mentioned, this is although we are saying this v as an attribute, and this thing 1 plus 2 plus t1 plus value is an expression. So what happens? First is, let's see, when we say past logical plan. So this is now getting translated into a logical plan. So how it is mapped is, see, this sum, this v was an attribute, but summation of v is an aggregate. Select in terms of planning wise, it is a project expression. So this project node is there. Then we have from T1 to join T1 T2. So this is the join. We have where clause, so the filter, and then we have the scans. And this is also how the logically how things will happen. First we will do the scan, we'll do the join, then we'll do filter, project, and then aggregate. Right? This is the sequence that we have defined in here as well. Uh, so we join, we filter, we add a column, we select that column, and then we aggregate it. That's the whole flow that is defined in here. So if this is how the tree structure will look like as of now when this logical plan is created. And if you see the past logical plan, if we write this explain command gives this. So looking at this as of now, if you see, there is no identification of which data type, what column is of what data type and stuff like that. This is still just a logical plan. Then we do an analysis of this plan, and then looking at the catalog information and everything, we will find out, okay, that id is big int and the sum will be a big int. So this information is present in the analyzed plan, not on the logical plan. So this is one difference. And same way, if we come down, uh, we now have an optimized logical plan that gets applied to this. And what happens in here is, for example, there are two rules, as I was mentioning in my last video as well, that there are 75 plus rules that gets applied. Uh, Two of them rules are predicate push down and column pruning. So let's see how it gets applied. So this was our original plan, right? Forget about the aggregate as of now. This aggregate, we are only interested in this part because that's where these rules are getting applied. So if you see, we had project, we always read this from bottom. So we had scan, and then we were doing a join, and then we were doing a filter, and then we were projecting. But now, because of the predicate push down, this filter is getting pushed down to these two, because we are saying t1.id is equal to t2.id. So that means both t1 and t2 are same, and we are saying t2.id is 5000. So definitely, if the IDs are same, and we are saying that from the left side, this sorry, left or right side, any side, we are saying that, okay, ID should be greater than 5000. So that it makes sense that, okay, while reading itself, we filter out all those records which are greater than 5000, right? And that's where this predicate push down is happening. See, earlier filter was happening after the join. Now scan, filter, uh, greater than 5000 and greater than 5000 on both side, and also is not null is added, because this is a common this is an extra rule that gets applied every time when we are trying to uh, do any comparison or something, because nulls will be ignored, right? That's why it says is not null. So we are not comparing anything which is null in this part. So this rule gets added automatically. This will happen. You will see not null filter getting applied everywhere. Whenever we are doing, when you do an operation equality check or which is not null safe, so that filter gets applied in here. So in this case, the predicate is pushed down. So now only certain less records will be picked up and then goes up. So this is one set of optimization that happened. The other one is, if we see in the query, we are only interested in certain columns from the right side. Not all columns are needed. So the plan was, oh, sorry, where is the SQL? So we are saying select some V. So only thing that we are interested in as of now is the T1.id and the V, right? Other columns from T1 and T2 are not at all needed. So we are going to filter that out. See here. So here, while scanning, we did uh, we were getting all the columns. Now here we will remove that column. See here, project, we are only getting the t2.id, nothing else from this right side, because everything is that is needed is coming from the left side. So this project has been even, so as one extra node of projection has been added, so that while we do the scan, after doing the scanning on the row wise, we also remove one column. We remove other columns, only keep one column, so that becomes one another what you called optimization that has happened. And if you see in the optimized logical plan, so earlier we have only logical, see the filter comes up in here is not null and greater than one. Again here we have one filter for greater than and not null, and then we also have a project which say that okay, what we are trying to project, so everything else goes away, join when also there. So this is another like optimization that happened at the catalyst layer. And so this is how the flow works. As I mentioned earlier, this tree execution keeps on happening recursively. So logical tree rules are executed, a new tree is created, and then again logical optimization keeps on happening unless we have a physical plan. And so this strategies are what makes the logical plan go into a physical plan. So when we say physical plan, so as of now here you say this projection, join, filter, there is no concrete implementation as of now. It simply says that we have to join, but how we will join, that is not decided yet. That's what it happens using the strategies. So Spark Planner will provide the strategies that what needs to be done for this case. Now we see again the full flow. Now what will happen is see the scan, how scan identities are now actually translated into Parquet scan, because one side was Parquet, JSON scan because the other side was JSON. Then filter, filter is plain simply and then project. Then we have sort. Why we are doing a sorting? Because we will be using sort merge join. So hence, since we decided on doing a join of implementation of that was sort merge join, there is a sort phase sort step was added in here. Then we have again filter, and this filters, this is done just to be on the safer side. Although there will be no record coming in here, we have already filtered these things in here. This is done as a fail safe. What if there is no predicate push down feature available to the data source? Let's say if the data source does not allow us to do a predicate push down filter, then we can't use this. So that's why there is a safe, what we called a fail-safe mechanism is added, that we added this filter still, although it will not filter any records because it's all are filtered down below itself. And then we do the project, and while doing the summation, the aggregate function has not been now been calculated as hash aggregate. In last video I was mentioning it can be hash or sort. This time we decided to do an hash aggregate. So this is the concrete implementation of this part, and this is the plan will look like. Physical plan will look like. And this see, if we have AQE enabled, it will say is final plan true or false, because AQE runs after this, right? It will decide at the runtime, it will decide whether this plan is getting executed or something else has happened. That's why is final plan is set to false. Once this is done, once the job runs, then we will see the actual plan that gets executed. So this is very important to notice when you have AQE enabled. Don't just look at the plan, look at whether this was the plan that was getting executed or not. So as of now, it's final plan. It says no, because it might do an extra optimizations from the AQE side. We will see AQE in our new video, upcoming video as well. So this is how the till now we have seen the physical plans are calculated. Now, as you were aware that in the last thing we have said that once the physical plan is calculated, all the relations are approved and joint strategies are taken care, then we whatever plan that gets executed, it goes through a whole stage code generation part. So that's what will happen now, and the tungsten execution engine will do that for us. Whole stage code generation will happen, and how that happens is as we know, whole stage code generation simply creates one big function which takes everything of that particular stage into a into an account and creates a function. If we want to look at the code that was generated, although it's a very big code that comes out, but yes, there is an option. Well, let's say if you want to see what was the code used to run this program, so we can say df.queryexecution.debug and then code gen. If it is there, it will emit that code that was generated. And how, see in this case, how this code generation is happening is, so let's say we had a scan, filter, and project. So see the scan gets translated into a while loop. First is consumption. So this scan is a total big while loop. Inside that itself, while this will keep on happening till table has next items. And then we have filter. So filter is again, it will see if the row dot get item, whatever is there in the second column is less than 36 or whatever, less than 200 or any number. So whatever filter that we applied, again it's a if block. Inside that, then we have a projection. So again, this projection, what it says is how do what to do with that. So it says uh, get string and get ID or whatever is there, and then it will return that row back to the caller. So eh, this is how one big function. This is although these are different stages, it's all gets translated into one single Java function, and that is consumed by the engine to run the code. So this is what I meant with whole stage code. So this whole stage has one single Java function that is doing the work for us. So that's what the whole stage code generation means. And this is done by compiler. As I mentioned last time also, I think it is Genino compiler. I think the version is version not sure 3 or something should be there. So this is how actual this thing select this SQL query or a data frame query uh, gets translated into what should be running in here. So this is basically how the flow works. And in the next video that I will upload, I will discuss about where does AQE comes in and how that changes the flow. Not changes the flow, but how it will act and create newer plans or adapt the plan to suit the requirements that we have. So yeah, that's it. Thanks for your time. Take care.